Okay, everybody. Today, what we're going to do is talk about the pumping limit for regular languages. So, not all languages are regular. Not everything can be pushed into that kind of regular expression or finite automata sort of way of thinking. And it is useful for us to have some things that we can say about regular languages, and that will help us prove things are not regular. And so, this is kind of the non general form of the pumping limit for regular languages, which makes things easier for us to talk about. So if a language is regular, then it has some pumping length p. Now we talked about this a bit in class, but it's the number of states in the machine that describes the regular language might be the pumping length p, but it's basically kind of one more than the longest string that doesn't have a star or doesn't repeat in some way. The pumping length p for us is going to be an abstract notion when we're using this pumping lemma, but for any specific regular language, you can actually clearly define what p is, and we took some time in class to do that. So if L is a regular language, it has some pumping length p, and every string that's in L, every string in the language that has a length at least p, can be written in the following way. So it can be written such that the string is divided into three parts, x, y, and z, with the following conditions. And really, this is about finding some loop in the machine where y is the path of the loop, this y part. But x, y, and z are just three different individual substrings of the full string w. So if you took the full string w and you cut it into three pieces, that middle part y is the substring that is the thing that you can take away and stay in the language, or add as many times as you want and stay in the language. But formally, there are three rules about this substring, and they largely center around what y is doing. And so when you're thinking about the pumping limit, you're often thinking about what is y doing. So for step one, the length of y has to be greater than or equal to 1. In other words, it can't be empty. It has to have some symbol in it. Step two, the length of xy has to be less than or equal to p. In other words, and this is what makes this the non-general version of the pumping lemma. In other words, whatever's looping has to loop in the first p symbols. And that is because the pumping length being equal to the number of states in the machine means after you see some p symbols in the machine, you must have returned to some state at some point. And so y itself has to be within those first p symbols, including whatever's in y. And so the reason we say the length of xy here is because x is kind of the beginning of the string before the loop, y is the loopy part, z is everything after the loopy part. And there could be multiple loopy parts, but you only have to find one, and there will be one if it's a regular language and the string is of length at least p. And the last part is the pumping part, which is that we should be able to take y away, and that would give us kind of our w0. And we should be able to add y as many times as we want, which kind of gives us whatever our wn's are. And all of those strings, w0, wn, if we choose the correct loopy part, have to stay in the language L. So if L is regular, then any string of length at least p, then there exists some y that will allow this all to happen. Now, you can't just pick the y willy-nilly. You have to pick the thing that's actually looping in the machine. But there will be a y that exists. So how are we going to use this? We use this to prove things aren't regular, okay? So the simplest language that we can prove is not regular is the one that has a number of zeros followed by an equal number of ones. So that's this language L1. And we want to prove that this thing is not regular. To do that, we're going to assume that it is regular, and therefore it has to obey this pumping lemma that we just talked about. Now, you haven't gotten a lot of time just from the video to kind of intuit how this pumping lemma is working, so I'm just going to kind of show it to you, and then we'll keep working on it, and hopefully you'll get there. Any string that's long enough, of length at least p, has to be pumpable. So let's choose a string that's definitely long enough. Let's choose a string 0 to the p, 1 to the p. Now, sometimes when using this pumping limit to prove things aren't regular, coming up with this string here is actually fairly challenging. It is not necessarily the easiest thing in the world, and so it is something that takes a little craft. And generally, you want to do your best to try to make the beginning as long as possible. Make it p symbols long if you can. So we choose 0p, 1p. It is length at least p. It is a length 2p. And rule number 2, if we look back up here, rule number 2, the length of xy has to be less than p, less than or equal to p. Rule number 2 says that y has to come from the first p symbols. And the first p symbols in this thing are all zeros, which is part of the reason we chose this string, is so that y does have to come from all zeros. And that's very, very interesting, okay? So we have to prove that no matter what choice of y that we make in this first p symbols, that it's not pumpable. And if we can show that there's no way to pump any choice for y, then we can show that this language doesn't actually obey the pumping lemma for regular languages. And using that contrapositive or proof by contradiction, we've then shown that our original assumption that's way up here must have been wrong, right? So what we need to do now is say, hey, no matter what choice you make for y, consider all possible choices for y. None of them will work. So one thing that we do know is that y comes from the first p symbols, and we also know from rule number 1 that y can't be 0, like length 0. Y can't be the empty string, okay? So y must contain only zeros and at least 1 0 from rule number 1. So if we look at 0p, 1p, that means y is some number of zeros just in general. And if we pump down, we're going to remove some number of zeros. So when we look at w0, the string that we get when we remove the y, then it loses some zeros. We could also look at w2, which is the string that we get when we add a y, which will gain some zeros. So no matter how many zeros y had in it, we think of all possible y's that could have existed, which could have been any number of zeros from 1 0 all the way up to p zeros. No matter what it had in it, W0 couldn't possibly stay in the language. It couldn't possibly still have an equal number of zeros because we're removing zeros without removing any ones. And the original language was an equal number of zeros and ones up here, right? They had to be equal. And so when we remove some of these zeros, we're left with something that is not in the language, right? And this is a contradiction, which means our assumption must have been incorrect, and L1 must not have been a regular language. Um, and I think there's a little more that we could write here, and we could say things like by contradiction and things like that. But this is the gist of how we're going to use the pumping lemma. This needs more examples before you're really ready. But this is something that you can look back on and kind of start to understand how this is working. So I'm going to stop it here, keep this one short. Hopefully this gives you an introduction into how this pumping lemma is going to work. If you're used to proofs by contradiction, this is probably not incredibly new, but this is a little bit different probably than things that you're used to looking at. All right, that's it for today. Good luck.